So this you are referring to the circular motion chapter, right? From H.C. Verma, Siddharth. Okay. So let's start with this question. Just give me a second. I'll go through the question once and explain it. Okay, so the question says that there is a block of mass m kept on a horizontal ruler. Coefficient of friction between the ruler and the block is mu. Ruler is fixed at one end and the block is at a distance L from the other end, from the fixed end rather. And the ruler is rotated about the fixed end in the horizontal plane through about an axis through the free end. Okay. Second part, if the angular speed of the ruler is uniformly increased from 0 at an angular acceleration of alpha, at what angular speed will the block slip? Okay, so this is a situation when the required friction to maintain the acceleration for the block, maintain the net acceleration for the circular motion of the block, that required friction reaches the limiting value. Okay, so if we take a vertical top view of the ruler, okay, so let's say that's like this. So it's rotating about this axis, okay, and our block is sitting somewhere over here. So at some time t, let's say it has an angular velocity omega and an angular acceleration alpha. So given the situation in part B, initial angular speed is 0 and alpha is uniform. So therefore omega at some time t will be alpha t. Okay. So the block will have an acceleration, provided it's not slipping, of centripetal plus tangential acceleration. Okay. This we are looking at it from the inertial ground frame point of view. Because non-uniform circular motion, we generally view it from the inertial frame so that we don't have to put two pseudo forces. So it has a component of acceleration like this and a component of acceleration like this, the block. Okay. So the net acceleration will become the vector sum of these two. It has a centripetal acceleration and a tangential acceleration like this. So the net acceleration is going to be in this sort of direction. Okay. So let's say this is the net acceleration vector. So this net acceleration has a magnitude of this much. Okay. So that is so as a function of time, that is the magnitude of acceleration. So the friction acting on it will be along this vector only. Okay. So the static friction acting this kind of expression we'll get. Now, this static friction should be less than equal to mu n, and n is equal to mg, because if you see the side view, you will understand that this is like the top view. So this is the limiting condition. Okay, this one here. So at the time at which this inequality converts into an equality, that is when it's ready to slip. I hope this is clear, Siddharth. Okay, very good. Any other doubt from this exercise, anyone?
Sir, I'm actually out of Mumbai at the moment. I don't have any materials with me except for my notebook.
Okay, okay. So when
So
are
I will
you?
be returning today. Today before Hemant sir's class.
Okay. Okay, so there is one question from this H.C. Verma that I want to discuss. I'll tell you the question number for those who have the book, otherwise I'll explain the question. Yeah, it's question number 27. Okay, I'll explain the question. So there is like a cylindrical, like an open hollow cylinder kind of thing. Okay, fixed open hollow cylinder. Okay. Now the floor of the cylinder is smooth, or you can just visualize this like a cylindrical room. Okay, a room that has a circular floor and cylindrical walls like this. Okay, so this is a smooth floor, whereas these are rough walls. Coefficient of friction is mu. So this is a fixed cylinder like this. Okay, now a particle is kept on the floor over here, let's say, against the wall. So this particle is kept over here. Initially at rest against the wall. Now it's given a tangential impulse, so that at t equal to 0, it has a tangential velocity v naught. So it starts going into a circular path like this. Now, as it goes against the wall like that, it's going to scrape against the wall. So kinetic friction is going to act. So as a result of that, it's going to, generally speaking, slow down. So after some time, if we look at the magnitude of its velocity or its speed at time t, v should become less than v naught because of the friction acting on it. So what we want to do is, given that the radius of this bottom is r and the coefficient of friction with the wall is mu, okay, of course the particle's mass is m, acceleration due to gravity is g. So first of all, find all contact forces. So when I say all, you have to be careful and understand how many contact forces are acting on the particle. So find all contact forces as a function of time. Or first, what we'll do is, as a function of v. And from that, we will find v as a function of time. And we'll also find v as a function of theta, that is angular displacement. So a bit of application of calculus in kinematics of circular motion will come into play over here. So at some time t, if the angular displacement has become theta, so in terms of theta, what is this angle? What is the speed of the particle? Okay, that we have to find. Try this question if you haven't before, quickly. Okay, so as usual, start with the free body diagram. So understand the FBD in 3 dimensions over here. In the vertical view, like the top view, what kind of forces will be acting, as well as in the side view, what kind of forces will be acting. So first of all, you have to realize that apart from the free body diagram and forces, once you solve the FBD, you need the acceleration because there are self-adjusting forces. So you have to understand that it is in a non-uniform circular motion with tangential deceleration. Now the particle state of motion is a non-uniform circular motion, okay, in the horizontal plane of the floor, okay. But because it's scraping against the wall, so the friction is against the velocity. So opposite, tangential and opposite to the velocity. So it has a tangential deceleration. Okay, so there will be in all three contact forces, right? Two normal reactions and friction. The floor will be applying only a normal reaction, whereas the circular wall will be applying a combination of normal reaction and friction. So at any instant, if you look at the side view, you see this, and you see the wall applying a centripetal type of normal reaction. Okay. But if you see the top view, you see that the wall applies a combination of two contact forces. Like this. Again, I'm looking at this from inertial frame point of view. Okay, so we have N1 balances mg and N2 is equal to m omega square r or mv square by r. Kinetic friction is equal to okay. So these are my three contact forces as a function of v at some time t. So from the above diagram, we can see that there is a tangential deceleration because of friction. So from this equation, we have to get v as a function of time and v as a function of theta. That is your second and third part, respectively. So now it's a matter of calculus. So solving this as a function of time, this is the integration we'll have to do. Now, third part, you have to rearrange this differential equation and solve v as a function of theta. So hint to use, you can use chain rule. Okay, for doing that, use chain rule and rewrite your tangential acceleration as something else in terms of v and theta.
Sir, noted.
Yes, that's correct, Siddharth. Okay. So there are different ways of doing this third part, but probably the simplest way of doing it is that since we understand that uh, V is equal to R omega, so ds is equal to R d theta, where V is rate of change of distance and omega is rate of angular displacement. Okay. So tangential acceleration, which we write as dv by dt, we can write as v dv by ds, and further write that as v by r dv by d theta. So this becomes the important thing. So we had above our tangential acceleration was minus mu v square by r. So now we can write this as this step here by substituting this here. And then we can integrate this. So this will give us the v as a function of theta. Okay, so this is just one easy trick of solving the problem, that using this relation, you can write your tangential acceleration as this. Okay, so that's about this question. Okay, now, before I move back to questions of vertical circular motion, I also want to discuss something about general curvilinear path, instantaneous radius of curvature. So this is now moving outside the domain of pure circular motion.
Then so this is not in NCERT.
No, this is not in NCERT. General, this is specifically used in JEE type problems.
Okay, sir.
So this is more like it's part of kinematics, and we'll also use dynamics eventually in this. Okay. So if we have any general non-straight line path, okay. So curvilinear basically means that any path which is not a straight line path. Okay. So in that, what happens is that there is, so if, for example, the path of a particle is something very general like this, it's going like this, then at any point of time during its motion, whatever the speed be, whatever the rate of change of speed be, if we take a differential section of its path and drop to normals, we can show that that differential section is part of some instantaneous circle. And that circle will be changing with time. The center of curvature will be changing with time. The radius of curvature will also be changing with time, unless it is specifically a circular motion. In that case, the radius of curvature and the center are fixed. So for example, at this particular instant of time, this is what the instantaneous radius of curvature is. And this is where the instantaneous center of that instantaneous circle is. At some other moment, it will change. When it is here, let's say, at that point of time, its instantaneous center of curvature might be here. And if the turn is sharper compared to that one, then the radius of curvature will be less. So here it's, let's say, r prime. At some time t prime is at some time t. So now there are two things. We can understand the instantaneous radius can be calculated from the instantaneous velocity and acceleration, or it can be calculated if the equation of trajectory, that is a path, is known.
So what did you mean by sharp turn?
If the turning is, see here, the curvature is such that it's turning more sharply compared to here, it's turning more smoothly. Then here the radius of curvature r prime will be less than the radius of curvature r over here.
So I'm trying to understand what it means in terms of omega and theta.
It's more like, yeah, in terms of omega, the rate at which the theta is changing. But see, again, omega is about with respect to time. But here, the sharpness of the curvature is more about with respect to position. You understanding?
Then so theta will change at a much faster pace, something like that.
It's like, you just compare two circles, one having a radius less than the other. So the path is turning more sharply in the one which has a lesser radius.
Okay, sir. Okay, I got it.
Understood? No? Yeah. An extreme example is on a road. You have a straight line path which is not got no radius, so it's got no sharpness. Okay. Then you come to a sharp turn. Just a minute. Yeah, so imagine you have a straight road like this. Then there's a very sharp bend. And then gradually it turns like this. So here the radius of curvature will be very less. It's a sharp bend. Here the radius of curvature is tending to infinity because it's a straight line.
Yes, sir.
And here again there is some turning, but it's not as sharp as that point. So the magnitude of the radius of curvature also tells you whether the curvilinear path is bending sharply or comparatively more smoothly.
Okay, sir. Okay.
Okay. So there are two ways of calculating the instantaneous radius of curvature. One is if we know the equation of trajectory. Now this is something quite advanced, okay, and typically for more tricky type of situations in JEE Advanced or Olympiads. So if we have, for example, we have defined our trajectory in the XY plane. So we know the equation of trajectory as y as a function of x, just like the parabolic equation of trajectory in projectile motion. Like that for any general path in the XY plane. Suppose, this is general path of a particle. This is the trajectory. For a moving particle. And at a particular point like this over here, we want to find the instantaneous radius of curvature. So what we'll have to do is like just think in terms of your geometry that at this point, x comma y, this is the tangent. So we draw a normal. It's nothing but a line perpendicular to the tangent. This is the normal at that particular point P. So if the particle is over here at some time t, this is the instantaneous normal. Now after some time, now I will take that time to be very short, but I will show it with quite a large amount of distance over here. So this is at time t plus dt. So imagine dt is actually very short. So the second point is very close to the first point. So again, at this point, if I draw a new tangent, slightly like this, compared to the earlier tangent, it's curved. And therefore, if I drop a new normal, slightly bent with respect to this one. Okay. So this one and this one will intersect finally at some point. And that point where they intersect, that is nothing but the instantaneous center of curvature. So basically, you have to imagine that in my diagram, these 2 points are very close to each other. So the distance between these 2 points, which is like a ds, is like a circular arc about this instantaneous center of curvature. This is the angular displacement d theta, and this is like a ds. So this is like this. For that dt being small, you have ds is equal to r d theta, this relation. So from this, we want to calculate the value of r. Okay. So I'll just zoom out of this now. Okay. Now, coming to this diagram again, from a different point of view. So if at a particular point I draw the tangent, that tangent is making an angle theta with the x-axis. So we know that tan theta is equal to dy by dx. This point is x comma y. So that is equal to f prime x at the point x equal to x. Now if I draw a second tangent at a second point, where this is x plus dx, y plus dy. So this angle also changes to theta plus d theta. So differentiating this, we have this, right? So we have sec square theta d theta by dx, okay, by chain rule is f double prime x. So we have d theta So now from here, you can see that we have R is equal to ds by d theta. So we are going to connect this equation with this equation somehow. And how we are going to do that is ds. Now basically see what in general S is equal to the displacement. So it is delta x I cap plus delta y j cap.
Yes, sir.
So in a small time, the displacement is dx I cap plus dy j cap. So the magnitude of the displacement in a small time is the same thing as the distance. Okay, for dt tending to 0, distance is the same thing as magnitude of displacement. So that is square root of dx square plus dy square. So that I can write as dx So I can write ds as dx into square root of 1 plus tan square theta. So now this, and this have to be connected. Okay. So just write down up to this point and then we'll continue further. And finally, we'll substitute tan theta as f prime x. Okay, so we'll see that we'll get the radius of curvature in terms of the derivative f prime and the second derivative f double prime at a particular point. So ultimately, it's a purely geometrical function for a given trajectory. It depends on the equation of trajectory, how sharp the turn or how smooth the turn at a particular point is. So that actually then depends on the derivatives, the first and the second derivative of the equation of trajectory, y is equal to fx.
Sir, also, sir, here it seems that the radius of curvature will not depend on
Come again, will not depend on?
the value of x from where we are calculating it.
It will now, because the derivative of the function depends on the value of x. Now, f prime x is a function of x itself. So is f double prime x in general. You know? Okay, so now let's connect these two equations and let's see how the radius of curvature works out. So first, see, we have r is equal to ds by d theta. I'll substitute ds from here. So it is dx square root of 1 plus tan square theta. And substitute d theta from here. So it is f double prime x into dx upon 1 plus tan square theta. So it just becomes 1 plus tan square theta. When this goes to the numerator, this power will become 3 by 2 divided by f double prime x. Okay. Now, one more thing we have to understand here, that geometrically radius is a positive quantity. So you'll have to take mod of this. Even if f double prime is a negative quantity, d theta by dx might be negative. Okay. But when we take r, it is like a mod of this thing. Okay. So you have to take mod of this. Okay. And of course, tan theta is f prime. Okay. So we have a relation of radius of curvature in terms of the equation of trajectory, that it is or we can also express it like this, that looks like a bit of a monster equation, but you apply it in a couple of questions, you'll get used to it. This is the instantaneous radius of curvature.
So can you explain the mod part again?
Yeah, I'll explain this. Okay. For a given point on a trajectory, y is equal to fx. Yeah, the mod part is like this, because second derivative, for example, if you have a curve going like this, so at this point, what can you say about the second derivative? You can see the slope is increasing. So the second derivative is positive.
Yes, sir.
Okay. But if I have a curve which is like this, for example, okay, then
Yeah, okay, sir.
second derivative is negative. Okay. So what if you take r with a algebraic sign, what it basically means that here the center of curvature is somewhere here, whereas in this case the center of curvature is somewhere here. But r is a radius of curvature, so it's a mod quantity. So it doesn't matter whether it's above or below. We always take it without algebraic sign. So we have to put the mod in the second derivative.
Yes.
Okay, so the interpretation of this equation, finally what it means, that for any given curve y is equal to fx, at any particular point on the curve, if I want to find the instantaneous radius at that point, then this is how I find it. Okay, I find the derivative of the function at that point. I find the second derivative of the function at that particular point. Find the values of dy by dx and d2y by dx at that particular point and substitute them in the formula. So that gives me what the instantaneous radius at that point is. Okay, so let's look at a quick sort of application of this. So if a particle is moving on a path like this, this is the equation of parabolic path. So let us say this point here
Y square is equals to 4ax, right?
the general equation of parabola y square is equal to 4ax time. Okay. So I'm taking a specific case of that. Okay. So the value of a is 3 over here. So this point is A, this point is B. And of course, it also passes through the origin. So find the instantaneous radius of curvature of this trajectory at A, O, and B. So one thing you'll understand is that before you get into differentiation and all that, you have to treat the equation of trajectory like a function, and this is actually not a function because y is equal to plus minus of root 12x. So there's that problem. Okay. So you have to divide it into two functions. The part of the trajectory where y is positive and x is positive. So that is one particular function. Okay. The path of the trajectory where it comes below the x-axis. So y is negative while x is positive. So that's another separate function. Okay. So the point A lies on the first function. The point B lies on the second function.
And so what can we say about the slope here? Is it increasing or decreasing?
That you can see from the graph better. What is happening is now the sharpness of the turn is maximum at the origin. And as you move away from the origin, it's a smoother and smoother turn.
Yes, sir.
And as you go towards x infinity, you can see it's like the radius of curvature will also start tending to infinity. But that again is something that also the derivative will give you an idea about.
Yes, sir.
Now for calculating the derivative, you can use a number of tricks, including chain rule and all that. You can just differentiate both sides with respect to x instead of first taking square root, then differentiating. That doesn't matter. But yeah, if you go with a very technical method of mathematics like that, so first you have to understand that the given equation is not a function. So the question of derivative does not arise till you actually express it as a combination of two functions. Okay, so at y greater than 0, x is obviously greater than 0, and we'll isolate out the point 0, 0. Y is equal to root 12x or whatever, 2 root 3x, like this. Okay. So dy by dx okay, this is correct. So what about second derivative? Like this. So at the point x equal to what we are taking 3. Okay. So at x equal to 3, y equal to plus 6. The value of dy by dx is 6. That is the thing, see that because of the mod, na, we have to take r without sign. This becomes how much? 1 by 6, correct?
Then, sir, for when we are finding the f prime, which we get as minus 6 by y square, instead of substituting x, we'll substitute y.
Sorry, come again. When we are calculating f
When
prime.
we're calculating, no, f double prime x, then.
Yeah, so I'm just taking the mod of it, no?
Yes, sir, but the value of, we won't be substituting the value of x, right? We'll be substituting
We have
y.
substituted. No? d2y by dx square at x equal to 3 we have calculated. See?
Then, sir,
Because
why
I
have we
want,
specified for y positive?
sorry, for?
Why have we specified that we're taking this for y positive?
Yeah, because see this thing, no, y square is equal to 12x. It has two solutions, no?
Yes, sir, but the value will be the same, no? For y is equal to minus 6 and plus 6.
What value will be same, madam?
So f double prime x.
It will not be, no? See, x to the power 3 by 2.
Yes, sir.
So for plus minus is different, no?
So, but x is only equal to 3, no? We're getting two values of y for that.
Yeah, that's okay. Okay. That is correct. Okay. No, but just a second. See, this is plus root 12x. Okay. And another solution is minus 12 root 12x. No? So these two will have different second derivatives. No?
Right. Yes, sir.
So one of them will give you a second derivative with a plus sign. The other one will give you a second derivative with a negative sign. Because you can see the shape of the graph. No? For this one, the derivative is decreasing. And here, the derivative is increasing because it's going from, let's say, minus 3 to minus 2.
Yes, sir.
Understood, no? Okay, so anyway, so the value of the radius of curvature will become So dy by dx was 6, right? So 1 plus 36 to the power 3 by 2 divided by mod of second derivative is 1 by 6. So it's very awkward kind of value we are getting. That is the instantaneous radius of curvature. Just a second. I made some mistake with this, is it? Okay. Yeah, correct. Wait, there's a correction here. dy by dx kitna hai? It is root 3 by x. Sorry. So at x equal to 3, it is 1 minus. So let's just make a correction here. Yes, correct. So the radius will be 12 root 2. Now we'll see. So this is at the point A. Even at the point B, it will be the same because of the symmetry. But if you don't take the mod, then one of them will give you with a negative sign and the other one will give you with a positive sign. Okay. It's also very interesting to note what you will get at the origin. dy by dx's value at the origin will be 0. Oh my god, undefined. Okay, so it's a very sharp curvature. So we'll have to take a limit actually. So this
So it's
will be,
approaching infinity for me.
no, that is at x tending to 0. Okay, but the thing is that at x equal to 0, it is undefined.
Yes, sir.
So the problem is that, okay. So it becomes like this actually, 1 plus 3 by x to the power 3 by 2 divided by root 3 by 2 x to the power 3 by 2. And on this, so at x equal to 0, it is undefined. Okay. But if we take x tending to 0, we have to calculate what is called a limit in maths. We have to calculate this thing's limit. Oh, sorry.
So how did you cancel out the denominator, sir?
Wait. This thing is in the denominator. That's why it's cancelled.
Then, sir, it should be multiplied with the denominator of the numerator, right?
Wait. This power 3 by 2 now. It's in the denominator, no? You understood, no? So it will come in
Yes,
the
sir, yes.
numerator. Okay. So like this, correct?
Yes, sir.
So that is now you put the value of x as 0. So root 3 also cancels and we get how much? We get 6. So radius at x tending to 0. 6. And you can see it's quite a bit smaller than this. This radius is about how much? 12 into 1.41, like this.
So I'm sure I'm able to understand, sir, what it actually means when we say the radius is getting smaller and smaller.
It means this, that, this is the shape of the parabola. So if you take a small section of the parabola here and convert it into a circle, it's maybe a circle like this. But then next somewhere here, if you take a small section of it and convert it into a circle, it's even smaller in radius.
But sir, why?
That is the nature of the curve, no?
Yes, sir, but why is it behaving like this? What is happening that we're getting smaller and smaller circles?
That is what the equation is showing you, what is happening with it. See, the geometrically, the slope at any point and how the slope is changing. These are the two things, no? So the slope
Yes,
is dy by dx, and how the slope is changing from one point to another, that is the second derivative, no?
yes, sir.
So you can see the smaller the value of the second derivative at a given point, the larger the radius, no? So the smaller the value of the second derivative, what is happening? The more slowly the slope is changing. You understanding?
Yes, sir, yes.
For example, if you have a straight line, the slope is uniform at all points. So second derivative will be 0, no?
Yes, sir.
So when second derivative is tending to 0, r is tending to infinity. So instead of a straight line, if you have a slight curvature, it is almost tending to a straight line. So you can see the radius is almost tending to infinity.
Okay, sir, okay. And greater the f prime,
Ah.
double prime, the radius will keep on increasing.
Yes.
Then, sir, this means that to navigate the turn, negotiate the turn, we'll have to apply.
A more normal acceleration.
Yes, sir, lots of
In
centripetal acceleration.
general
Right?
curvilinear motion, we are coming to that point now. We don't call it centripetal acceleration. Okay. Though you can, because it points towards the instantaneous center of curvature. So it can be called centripetal also. But preferably we call it normal acceleration. That means it's a component of acceleration perpendicular to the velocity. So that component is responsible for turning the velocity vector. Whereas the tangential acceleration, if it is there, is responsible for changing the speed.
And so normally we're not able to make that provide enough acceleration, so the car will skid.
Exactly. So if you're going along a parabolic path like this at some speed v, and you want to successfully take that turn, then you must have that normal acceleration required for it. So
Okay,
how
sir,
to
okay.
calculate the normal reaction required at a given point? If you know your equation of trajectory, so the normal acceleration will be v square by r.
And we can find our.
Yes, exactly. Okay, so now that other point, B, you will see it's a symmetrical point. So the center of curvature is at a different position, but the radius of curvature will be the same. So B is that point where the y coordinate was -6. Okay. So the equation of the path would have been, minus of 2 root 3 x to the power half and all that. But when you do all that and you see the radius will come out to be the same. It will come out to be 12 root 2, same as at E, because they are symmetrical points. So I'm not doing the whole calculation because it's the same thing actually. When you take the mod of d2y by dx square, you'll see they have the same value. This radius and this radius will be the same. I mean, there's no guarantee that these two centers are having the x-axis as the common tangent or anything. Don't assume that. They could be any shape. They could be like this. Okay, so that's just to give you an idea. Now the other thing is, instead of this thing equation of trajectory, if we know the instantaneous velocity and acceleration of a particle, from the instantaneous velocity and instantaneous acceleration at a point in a particle's motion, curvilinear motion. So we don't know the equation of the path along which it is moving, but we have knowledge about the two vectors, the instantaneous velocity vector and the instantaneous acceleration. Then from that also we can find out the instantaneous radius of curvature. So let's say a particle is going along some path like this. So at a particular instant, the particle is here, let's say. And we know that the instantaneous velocity vector, know it in vector form. So we know the magnitude and direction of this vector. So obviously the direction will be tangent to the curve at that point. But since we don't know the equation of the curve only, so that's not of much use to us, that information. The velocity is along the tangent. It's not really of much use. But in addition to the velocity, now we also know the instantaneous acceleration. So if it's going along a curved path, the acceleration cannot be tangential because the velocity vector has to turn. Okay, so the acceleration has to have what we call a normal component. So this is the normal line, this is the tangent line. So the instantaneous center of curvature has to lie along this normal line, somewhere here, let's say. This is the radius of curvature. So if the angle between these two vectors is theta, then E sine theta is what we call the normal acceleration. Whereas A cos theta is what we call the tangential component. So tangential component is rate of change of speed, and normal component is v square by r, where r is the instantaneous radius of curvature. So for example, here cos theta, if you know acceleration and velocity as vectors, then this is the method you have to use to find theta.
So noted.
So for example, now you can apply this to a projectile motion, and instead of complicated differentiation of the equation of trajectory, especially if something is asked in terms of time, etc. So you project a particle with a given velocity, a given angle of projection on the ground, and you want to calculate the instantaneous radius of curvature at various different instants of its path. Suppose we have taken the initial speed as 50 meters per second for projection, and the angle of projection as 53 degrees at t equal to 0. And acceleration due to gravity is the standard value. So you want to find the instantaneous radius of curvature. T equal to 0. T equal to 2 seconds at the highest point of the trajectory. Okay, and then again at t equal to, let us say, 4 seconds. Or in fact, let's make this 6 seconds. So here the better option is to use the combination of acceleration and velocity, because it's easy to calculate velocity at different times and acceleration is uniform. Okay, so let's work this out. Let's say this is like this. Now you can see here that if you take the standard coordinate frame, then your initial velocity here is 30 I cap plus 40 J cap, and your acceleration is minus 10 J cap. So your velocity as a function of time is 30 I cap plus 40 minus 10 T J cap. So at, for example, T equal to 0, it's very simple. Your velocity vector is like this, and your acceleration vector is like this. This angle is 53 degrees. So you can see that this angle is 53. So G cos 53 is the normal component, and G sin 53 is the tangential component, which is minus dV by dt. Okay, so anyway, we'll concentrate on this. So 10 into 3 by 5 is equal to 50 square by R. So write this as R naught. Okay.
So we could have also found the equation of trajectory for the entire motion.
Yeah,
right?
we could have done that also, but then that d2y by dx square and all, like, it's lengthy now. So where, because especially at time 2 seconds or 6 seconds, you'll have to calculate the coordinate, then calculate the value of derivative at that coordinate and all that. So it's lengthy.
Yes, sir.
So this is the much easier method here. This is the radius of curvature at the initial instant. And for this, we didn't need to use vector analysis that much, because we just know geometrically it's easy to calculate the angle and all that. Okay. But for example, at t equal to 2 seconds, it is better to go with the vector algebra approach. Okay. So the velocity from this equation here becomes how much? It becomes 30 I cap plus 20 J cap. Okay. And the acceleration is minus 10 J cap. So the angle between these two things, the velocity vector acceleration vector, this angle is at that instant some phi, whatever. So we have cos phi is equal to dot product divided by product of magnitudes So this type of calculation we have to do. Now at the highest point, again, you don't need to do vector analysis because you can see the velocity has become like this, and the acceleration will be normal to it. Now the other point where t is 6 seconds is actually a symmetrical point to t equal to 2 seconds. So you'll see you should get the same radius of curvature. This is somewhere where t was 2 seconds. The highest point is where t is 4 seconds. So 6 seconds and this one should be symmetrical. So whatever radius you get here, same radius you should be getting here. Okay, so this is a typical example of application of instantaneous radius of curvature in this kind of situation. Okay, whereas now, for example, we had the previous question where we had that equation of trajectory given to us. Okay. This one. Now, in this, for example, if there is a particle which is moving along this path at some given uniform speed, let's say 2 meters per second uniform speed. Okay. And as it negotiates the turn at the origin, we want to find the acceleration the particle needs. We had this, okay, where x is in meters, y is in meters. So we want to find the acceleration vector of the particle at the origin. Okay, so then it's the other way around. Okay, we understand that the normal component of acceleration at the origin will be equal to b square by the radius of curvature at the origin, and the tangential component of acceleration will be dv by dt. So if it is going at uniform speed, then that is 0. So the acceleration itself will become the normal acceleration or uniform speed. Now from this equation of trajectory, we had found out that the value of this thing at the origin was how much now? It was 6 meters now. It was 6 meters. So the acceleration of the particle is this much. So that is a full application, okay, for this type of concept.
Okay, sir.
Okay, so with this, you should be able to negotiate any problem to do with tangential and normal acceleration in a general curvilinear path also, not just for circular motion. Okay, so it's a bit of an advanced concept, specifically for tricky questions in JEE Advanced or Olympiad style questions, not really at all for JEE Mains. This topic will not really be touched at the JEE Mains level. Anyway, so that's it
So
for today's session. Yeah.
So where can we find questions for it?
You will find some questions in the subjective exercise of your this thing of your module, and eventually
sir.
I'll also be giving some revision subjective questions from circular motion path. So in that I will include these questions. Okay.
Okay, sir.
Okay, sir.
Okay, so that's it for today's session. Next session we'll again do some revision questions of vertical circular motion with some variations of the standard case, and with that we will wind up this section and then move on to center of mass.
Bye, sir. Thank you, sir.
Okay.
Bye. Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.